Hey guys, today we're going to go over problem 716. This problem is asking us to find the internal normal force, the shear force, and the moment at point C of the beam. And point C is in the middle. So we'll start off this problem like we always should by making a free body diagram. We're going to do the whole beam first so that we can find some of the reactions and other information, and then we'll go ahead and slice it in half so we can look at just point C. Okay. So if we start by drawing the beam, then we notice here that we have these distributed loads across the top of the beam. But if you look closely, it's not just a triangle. It's probably easier if you break it down into two pieces, which I'll represent as this more rectangular shaped distributed load. And then on top of that, we're going to add on a triangular one. Okay, so since on the left side of the beam it says 200 newtons per meter, on the right side it says 400 newtons per meter, we know that the rectangular part is going to be 200 newtons per meter, and the triangular part, since that's just, you know, the extra part of the 400, then it's 200 newtons per meter. It's the difference between the two. This will make the problem a lot easier. Okay. Now, also, to simplify this, it becomes a lot easier if we also turn the distributed loads into like a point load. Now, in reality, this doesn't actually work, but in terms of solving for the information we need, this is perfect. So I'll go ahead and label this one. Say this goes in the middle, is W1. And then in the triangle, the center where the point load would act is actually 1/3 from the larger end, if that makes sense. So we'll put that right here. W2. Okay. Then to just add some more information, there's C, there's point B, there's point A. Okay. Then if we look back up here, at point A, we are going to have a force in the x direction and the y direction because of this joint type. So I'm going to throw that in there. And then at B, there's a roller, so then we just have a reaction in the y direction. Okay. So then we're going to want to find the distributed loads. And to do that, we need a little bit more information, which is the sort of like the distance that the distributed load acts upon. So if we want to look at W1 first, the rectangular load, we know that it is the 200 newtons per meter, and it acts on this whole length of the beam, which is 6 meters. Right? So we're going to multiply that by 6 meters. And that's going to give us 1200 newtons. And we do the same thing with the second distributed load. That's going to give us 200 newtons per meters times 6 meters. But since it's a triangle, we're going to throw in the 1/2 in the front. And that is equal to 600 newtons. Which is basically just half of W1, but it's good to do that extra step so you know why you're getting that number. And then what we'll do is, we don't need it right now, but I'm going to clarify that the distance between B and W2, we'll put that as x2, that is going to be equal to 1/3 of the whole beam length, right? Beam length, sorry, from, you know, point B to where the point will be to where the force will be acting is 1/3 of 6 meters is equal to 2 meters. And then if we want to get x1 from B to point C, it is half of 6 meters. And so x1 is equal to 3 meters. All right, So that's a good setup. And now we're gonna just start figuring out what the forces at A are equivalent to. So if you look back up here, if you look at AX, okay, we'll do the sum of the forces in the X direction, which are equal to 0. There's only one force in the X direction, so AX is equal to 0. Simple, easy. Okay, so then we're going to do AY. And to do AY, it's a lot easier if we take a moment. And I'll take that at B because I'm not sure what BY is, but I know what W1 and W2 are. We're going to have the positive direction going counterclockwise, which is pretty conventional. Okay, so that's equal to 0. And then from our free body diagram, we can see that if we do it all about point B, we'll have negative AY times R, the distance between A and B, plus W1 times X1, and then plus W2, it looks a little weird, times X2. And so the latter two terms are both positive because they're going in the counterclockwise direction around point B, right? Then if we plug in all this information, we'll have 0 equals to negative AY times 6 meters plus 1200 newtons times 3 meters plus 600 newtons times 2 meters. And that'll give us an AY equal to 800 newtons. Okay. Now we can take a look at the next part. And so to do this, I think it's best if you take a cut at the beam, but do it from the left side. Because the thing is, we haven't solved for BY, and honestly, we don't really need BY to do this, so it'll be a lot easier that way. Okay. Oh. I'll do it a little lower. So B1 and W2. Okay, so then here we're going to have point C, here we're going to have point A, and we'll draw the same things as we had before. We'll keep it the same way. AX, which we know is equal to 0, but I'll put it here anyways, and you'll see why. And we'll have AY. And then at point C, now because we cut the beam, there's a couple of extra things we have to do. To compensate for all the internal forces, we first are going to add a shear, and we're going to do that pointing downwards because that is conventionally what is the positive direction for shear. And then moment in a counterclockwise direction because that's what's also considered positive when it's on the right side of the cut. And then we have a normal force, we'll call that NC, and which is also, positive. But when we look at this, we know that the sum of the forces in the x direction are equal to 0, right? And 0 equals NC plus AX. And since AX is equal to 0, the normal force at C is also equal to 0. So then we can also take the sum of the forces in the y direction, and that'll help us find the shear BC. Okay, so we have 0 equals to AY minus W1 minus W2 minus VC. So then we'll have VC is equal to W1 plus W2 minus AY. And we know that W1 is equal to 200 Newton meter. Oh wait, sorry. Negative 200 newtons per meter times the distance it acts on, which is going to be 3 meters, since we cut the beam in half, right? Okay, so, and then we're also going to subtract, since it's a triangle, 1/2 of 200 newtons per meter times 3 meters, and that's for W2, right? Then we're going to add on AY, which we found earlier, to be 800 newtons. This will give us a shear equal to 50 newtons. Voila! Lastly, we're going to take the sum of the moments at C. Here, 0 is equal to MC, right? MC minus AY times 3 meters, okay? Right, the distance between AY and C, minus, plus W1 times 1.5 meters plus W2 times 1 meter. And so it's 1.5 and 1 meter because this distance right here, x1, is equal to half of 3 meters, which is 1.5 meters. And then x2 is equal to 1/3 of 3 meters, which is just 1 meter. And that's why we get those values there. Now if we plug in everything, we got AY is equal to 800 newtons times 3 meters minus 600 newtons times 1.5 meters minus 150 newtons times 1 meter. That's all equal to 1.35 kilonewton meters. And there we have it. So our moment at C is 1.35 kilonewton meters. Our internal shear at C is 50 newtons. And our normal force is 0 newtons.